Greetings YouTubers, and welcome to episode 9 of my ongoing series, Lies That Flerfs Tell. Today will be our third exploration of Oakley's favourite claim, Earth measures flat. Now I'm going to have to start this episode with a confession. I had previously believed that Oakley had some sort of justification, however tortured and irrational, for holding this position. But he doesn't seem to. Genuinely, this seems to be something he just vomits in front of his congregants and then just says variations of it is, it does, trust me bro. So, please allow me to offer my sincerest apologies. I deeply regret any misapprehensions rising from my misunderstanding. Oakley is not presenting any arguments in support of his position, he is mindlessly regurgitating a bland and demonstrably false assertion. Last episode I considered Oakley's claim that somehow distances across Earth's surface require that the Earth has a planar reference surface, and I was able to demonstrate that this claim is simply false. That in fact, distances across surfaces are well defined regardless of the geometry of the surface, provided only that the surface is smooth. Before that, we considered Oakley's claim that somehow elevation angles require that the Earth has a planar reference surface, and we showed that this too is simply false. To construct or measure angles requires only two rays, neither of which needs to correspond or intersect a physical surface. Today we're going to examine Oakley's claim that somehow elevation distances require that Earth has a planar reference surface. This claim seems to imply that somehow the distance between a surface and a point is well defined if the surface is a plane, but not otherwise. Impressively, this is the most idiotic of Oakley's claims, and as you can imagine, that's up against some pretty stiff competition. If Oakley had only bothered to look at the definition of geodetic height, the geodetic height of a point is the normal distance between that point and the reference ellipsoid. Correspondingly, geodetic elevation is the distance from the point to the geoid. We obtain geodetic elevation by adding the geoid-ellipsoid separation to the geodetic height. Geodetic elevation is therefore measured relative to an ellipsoidal surface, not a flat one. The fact that the geoid is not flat was explored in greater detail in episode 3 of this series, where data from geodetic surveying, gravimetry, satellite altimetry and GPS were combined to derive the shape of the geoid, with the result that the geoid is well approximated by the reference ellipsoid and is not even remotely flat. But there remains a central mathematical question. How is elevation above an arbitrary curved surface calculated? The distance from our target point to any other point is a simple distance function as we discussed last video. In this case, we want the minimum value of this function subject to the constraint that z is a given function of x and y. This is a fairly standard problem from Lagrangian mechanics, and the solution is obtained by constructing a new functional. A new functional is the sum of the distance function plus a multiple of our constraint. The multiplier of the surface constraint, here denoted alpha, is called the Lagrange multiplier. We can now take partial derivatives of our newly defined operator with respect to the variables x, y and z and the Lagrange multiplier alpha. The point on the surface that gives the minimum distance to our target point is then obtained by requiring that each of these partial derivatives be equal to 0 at the same time. We then have 4 equations in 4 unknowns. As long as these equations are linearly independent, the system is solvable. How we actually obtain a solution depends critically on the form of the function f, which defines our surface of interest. So we can immediately see that Oakley is simply wrong. Given an arbitrary smooth surface and a point exterior to that surface, we have mathematically robust techniques for working out which point on the surface is closest to the exterior point. Now this probably all seems very intimidating and unnecessarily complicated, but things get much more concrete in the case of an oblate spheroid. Now, I fully understand that most people listen to YouTube videos while they're driving or doing chores or that sort of thing, but this is not one of the videos where that's going to work. Unless you're some sort of geometric savant, you're really going to need to see the diagrams and the formulae to really understand the rabbit hole I'm about to lead you down. So let's get started. Oblate spheroids are smooth and strictly convex, which means that at every point on the surface of an oblate spheroid, there is a uniquely defined tangent plane. Now, since distance calculations are irrelevant to translations of the origin, we can choose our origin to be anywhere. In the case of an oblate spheroid, it's most convenient to choose our origin to be at the center of the spheroid. Distances are also unaffected by rotations, so we are free to rotate our coordinate system so that the vertical axis corresponds to the axis of oblateness. With these choices, the formula for an oblate spheroid becomes x squared divided by a squared plus y squared divided by a squared plus z squared divided by b squared is equal to 1, where a is larger than b. A and b are the lengths of the semi-major and semi-minor axes, respectively. The relative magnitudes of A and B give us the eccentricity of the ellipsoid, or how elongated it is compared to a sphere. Now let's consider a point P0 exterior to our oblate spheroid, whose coordinates are known. Let P1 be the point on our oblate spheroid that is closest to P0. Our problem then becomes, if we know the coordinates of P0, can we determine the coordinates of P1? The answer is yes, but it's a long and twisted journey, so buckle up. Basic geometry tells us that P1 has the property that the ray P0 P1 is orthogonal to the tangent plane at P1. The distance from P0 to P1 is by definition the geodetic height of P0 above the oblate spheroid. The angle at which the ray P0 P1 intersects the horizontal axis gives us the geodetic latitude of both P0 and P1. The distance from P1 to the point at which the ray P0 P1 intersects the vertical axis gives us what's called the prime vertical radius of curvature. This term has a very elaborate mathematical significance, but I'm not going to go into it here. We'll see why this quantity is useful in a little bit. Again, rotations don't affect distances, so when solving this problem we're free to rotate around the vertical axis, so that the points P0 and P1 both lie on the plane y equals 0. The intersection between our oblate spheroid and the plane y equals 0 is just the ellipse, x squared divided by a squared plus z squared divided by b squared is equal to 1, which can be rearranged to give us an explicit form for z as a function of x. This allows us to take the derivative of z with respect to x, which is the gradient of the latitudinal tangent to this ellipse. Since the ray from P0 to P1 is orthogonal to the tangent at P1, we know that the product of their gradients is equal to -1. Since we already know the form of the latitudinal gradient at P1, we can determine the gradient of P0 P1. Extending the latitudinal tangent to meet the horizontal axis, we obtain the complement of geodetic latitude. The trigonometric tangent of this angle is equal to negative the gradient of the latitudinal tangent, which is probably better understood if we write it out as a formula like this. From basic trigonometry, the tangent of the complement of an angle is just 1 over the tangent of that angle. So, since we know the tangent of the complement to the geodetic latitude, we can obtain the tangent of geodetic latitude. From this, we can derive an explicit formula for geodetic latitude, provided we know z and x both lie on the ellipsoid. Okay, so if we knew the coordinates of P1, we could work out geodetic latitude. Great, but we don't yet know the coordinates of P1, so how does this help us? It's one step on the road toward finding a solution to our problem. Going back to the first expression in our last slide, we can actually take this in a different direction. Cross-multiplying both sides and taking the square gives us this expression, which may not look that useful, but we have an additional piece of information. We know that the point P1 lies on the ellipsoid, which means that x and z satisfy the formula for the ellipse we were discussing earlier. This can be rearranged to give us a form for a squared z squared in terms of x. We can now substitute this expression back into our previous formula. This allows us to entirely eliminate the z squared terms and leaves us with an expression that only relies on x and geodetic latitude. We can gather all the terms involving x squared on the same side and reorganize to obtain an explicit formula for x in terms of geodetic latitude. Looking back at our original diagram, we can see that the x-coordinate of P1 is equal to the prime vertical radius of curvature times the cosine of geodetic latitude. So all of this mucking around has allowed us to get an explicit form for the prime vertical radius of curvature. This is the second step on our path to a solution. The same technique that we use to derive a formula for x in terms of geodetic latitude can be used to obtain a corresponding formula for z. We can extend these formula for x and z to points above the ellipsoid by just incorporating geodetic altitude. So now we have some expressions relating the coordinates of point P0 to geodetic latitude and the prime vertical radius of curvature. Finally, we can use the basic rules of trigonometry to derive yet another form for the tangent of geodetic latitude. Okay, so what? Where does that get us? Well, it turns out that this expression for the tangent of geodetic latitude is very closely related to our formula for z. So we can rearrange this formula and substitute back into the formula for the tangent of geodetic latitude. But this time, instead of using the coordinates of P1, we're using the coordinates of P0. And that's really important because we know the coordinates of P0. They were given to us in the formulation of the problem. That's all well and good. But this explicit formula for geodetic latitude also relies on the prime vertical radius of curvature and the sine of geodetic latitude, neither of which we know. So I know what you're thinking. You're thinking, what the hell is going on, and why is this cretinous senile old fart wasting my time? Patience, grasshopper, we have arrived at our destination. We can now use the coordinates of P0 to obtain a loose estimate of geodetic latitude, which in turn allows us to estimate the prime vertical radius of curvature. These results can then be combined to give us a new, updated, and more accurate estimate of geodetic latitude, which allows us to obtain a corresponding estimate of the prime vertical radius of curvature. And at this point, we've kicked off an iterative cycle in which we use the previous cycle's estimates to obtain new and updated approximations for each of the variables. And we keep on doing this until we've achieved a level of accuracy that we're happy with. This iterative scheme, or something very similar to it, is what your GPS unit will use when it's calculating your geodetic coordinates. Now that we have accurate estimates for geodetic latitude and the prime vertical radius of curvature, we can now move on to calculating geodetic altitude. This can be done by just rearranging our formula for x0, the x-coordinate of the point P0. Rearranging this expression allows us to directly calculate geodetic height. Geodetic elevation is then just geodetic height plus the geoid-ellipsoid separation for the given location. So I have shown in this video that, to the surprise of no one, Oakley is completely wrong. There exist well-established, mathematically rigorous techniques for calculating the elevation of any point above an arbitrary smooth surface. For the specific case of an oblate spheroid, there are particularly sophisticated techniques for calculating geodetic height that are routinely used in geodetic surveying and GPS observations, and from which geodetic elevation is directly calculated. Oakley's claims have therefore been demonstrated to be as utterly devoid of worth as he is. So that might do things for today's video. Thank you so much for watching, I really do appreciate it. At this stage, it seems incredibly unlikely that Oakley will update his cult catechism, so with any luck, none of us will have to pay attention to him or his idiotic utterances for the foreseeable future. So join me next time when I'll be discussing another Flat Earth favourite, you can't have triangles on a sphere.